So, how's everybody today? You can reply in chat. You can turn your microphone on. Feel free to ask a question at any point during this, please. I'm getting really tired of talking to myself. So I'll put a chat notification on when a chat pops up. So I will hear. Let me hear an audio. That'll be better. An audio notification. Let's see, add a audio notification when someone raises their hand. Let's see, any other audio notification when someone joins the group. No, I'll leave that off. Hey, we got a chat. I'm good. How are you? I'm doing okay. I'm feeling like a little disorganized today, unfortunately, and hopefully that doesn't cause you any pain and suffering as you hear me stumble through this lesson. It's not really a lesson. It's a review session. I like to have review sessions when I was a student, so that because of that, I try to hold them for every class that I can. But there's practice problems that have been posted, and I think most instructors have been posting those practice problems and the solutions. So because in another class I created for my mechanisms class, I put some velocity and acceleration review problems. I made those available. I was thinking about going over those, so then I can leave all the other old exam problems, and that's what those are, old exam problems. I could leave them to your so that you can use them. And I'm going to post the solutions to them pretty soon, I think. I usually throughout the semester, I start off with trying to keep the dynamic students working on their own instead of reading the solutions, and then throughout the semester I kind of ease up a little bit on that. So I probably will post those pretty soon. The solutions to them. I really encourage you to work through them yourself. So let me get rid of my ugly mug. I only put it up here so you know that there's actually a person. But I do want to show off my shirt here. All right, so this just came out. And I'm not sure how big this looks to you. Maybe if I get rid of my whiteboard, you will see how incredible this shirt is. It says Run Away. It looks a little bit like Run DMC, but it's got a rabbit right here that's got blood on it, right? So if you know Monty Python and the Holy Grail, it'll make sense. Otherwise, they'll just see it very random. And I'm also wearing a 30-year-old hat. This is the hat that I got on the this is my second year out at sea, the MV Paul Buck during Operation Desert Storm, and that's the ship I was on. So, hats. Exciting stuff. I know. You really don't care. That's okay. So I will share my screen and start going through some stuff. Once again, you could be watching a video instead of doing this. Because you instead of watching a video, you're here live, and so might as well get the benefit of that by asking questions. And you guys can't hear me, right? Just double checking. You give me a chat. Say yay, nay, yes. Okay, good. Good news. All right, so I will start going through some stuff. And first I will detach my Surface from my Surface Book and flip you around, and you'll hear me rustling and making noise. Hello. Come on, flip back over. All right, very good. Alrighty then. So, the title, ta-da! Review session for Exam 3 in Dynamics. The end is near. So, on this Exam 3, we're covering Chapter 15. years earlier, sometimes I would cover a little bit of the stuff that was in chapter 16 as well, but I'm limiting it to chapter 15. And the topics that we've covered since exam 2 have been rigid body motion, angular kinematics. We'll talk about what that means. And then we did a velocity analysis and acceleration analysis. So this is all rigid body motion, I mean by RBM, just so you know. And so if you're using the equation sheet that I provide, here are the fundamental stuff. And actually, I'm a big liar, so let me fix my lying. I can discard all that stuff. There was nothing interesting there. And let me fix this. Boom, right there. Because that's going to be there's nothing on there that is covered in not the, let's see, what did I just do here? Let me see. What did I just do? Mass center. That was weird. Oh, I know what I did. Okay. Apparently I didn't do this is what I meant to do. Yeah. There you go. Okay. I guess I didn't hit crop. That's what it was. This is totally unnecessary. I know. I don't want to waste your time. But I did want to get this correct, right? There you go. All right, so here is what we've covered since we last met, since we last exam. So when I mean as by angular kinematics is this stuff right here, where we have the angular velocity is the time rate change of the angle, and the angular acceleration, the time rate change of the angular velocity. But we also know that's the second derivative of the angular position, but also we have the wild card, the angular velocity times the time rate change of the angular velocity with respect to the angle. That's very, very, very much analogous to these guys over here, right? That's basically the same stuff. Did I just hear a hand being raised? Is that a hand being raised? No, I'm losing my mind. That's cool. That sounded like a ding, like a hand being raised. Or perhaps it was a hand being raised, and that was, let me see, boom. No, just some random noise. And another little bloop. Okay. Well, if you have something to ask, please use a microphone. Maybe that's the best way to go, because I don't know what's going on here. So anyway, other things that we covered, rigid body motion, the velocity analysis, right? So if we were going to treat it as a vector right here, remember that rigid bodies are a combination of translation and rotation. So right here, that's the translation, or the reference of velocity. If we want to find the velocity of B, we use some reference, and then we treat that like the translation of it, and then we incorporate the addition of the rotation. And the same thing true if we wanted the acceleration of B, we take acceleration of A, and then get a reference that's taking place in terms of rotation. And that rotation is broken down in acceleration into tangential and normal. And if we want to do cross products in it, and we're talking about a one plane, if we limit ourselves to 2 dimensions, we could take this part, that's the tangential, and this part is the normal, aka the normal is also centrifugal. Now, this part right here, this is really out of the class that's missing, class 18, if you were going by my class numbering schedule, and that's something we didn't cover in, so it's not going to be tested, but just so you know, there's the difference is that we would have relative motion going on right here, relative acceleration, and then this little guy right here, he's the wild card, he's also a wild card. He's the Coriolis acceleration, and he also appears in particles right up in here. So, and also, if we want to make that analogy right here, also this relative acceleration right here. He was represented by that r dot in particles. Similarly, this relative velocity right here is represented by this r dot right up in there. So anyway, that's the stuff that we've covered since the last exam. Sounds really simple, doesn't it? Well, it could be a little bit more complicated than that, actually doing this stuff. Here's problems, and I'll just talk through them. I won't work these out. I have the examples that I want to go through, or I suggest that we go through. We have angular kinematics here, where we try to figure out, with a constant acceleration, angular acceleration, these things speed up and slow down. I think this actually was a in-class example, but it was an old exam problem. And one of the reasons why I include old exam problems is so that now you can take a problem that was considered, at least at one point, short enough that it could be done in the class time, right, during the exam time. That means that now you should be timing yourself for, if you assume there's 4 problems typically on an exam, 75 minutes. You divide 75 by 4. And you should be doing problems in 18.75 minutes. So you should time yourself. And if it takes you 20 minutes to do a problem, you need to get faster. So do another problem and time yourself some more. Just like learning to run sprints. Here's a velocity problem. Sometimes I will ask a velocity problem and tell you a particular way to do it. So you might want to be able to do not only the ICR, but you might also need to be able to do the vector method. Here's an acceleration analysis. Quite often during an exam, I will give you the angular velocity of the parts, because in acceleration problems, we always have to do a velocity analysis, but a lot of times for exams, I'll break those up into different problems. So in one problem will be a velocity analysis, and another problem will be an acceleration analysis where the velocity analysis has already been done for you. And I kind of do that because some people might get stuck, not be able to do the velocity analysis, and then never get to the acceleration analysis. So I want to give you more an opportunity to focus on one aspect of the thing. So as you can see right here, in this particular review session or review package, you see they have S17, S17, S17. So you can consider those to be one full exam. So you might want to save that to the end. Here's S16, angular kinematics, S16, velocity analysis, S16, acceleration analysis. Look at that. So right there in the spring of 17, I had an exam that had those 3 questions on it. In the spring of 16, I had an exam that had these 3 questions on it for this topic. So that's like one complete exam each. By the way, those were for 60-minute or 50-minute exams, by the way. So you would, in the same way, you would have those should have been timed out as 50 divided by 3. And so those were 16.67 minute problems, right? Just to make sure you're clear, that's how much time it should take you to do it. Okay, so here in spring of 13 was a problem. I don't think these are all full exams. Here is a spring of 13 acceleration analysis. So I didn't do, okay, so I think it's the thing is breaking down now. Here's an angular kinematics. Here's a spring of 14 velocity, spring of 14 acceleration. You know, in this particular thing, I think this was a homework problem. So just so you know. Here's another rigid body angular kinematics. All right, so now these are not old exam problems. These are just suggested problems that a fellow faculty included in our review package. So these are just out of different books. And so here's where we begin with new problems that I'm going to work through. And I should probably do this in a couple different ways, right? So maybe I will do this velocity problem in 3 ways. So let me duplicate this and duplicate it. There you go. So the first way that I should do this is with vectors, and I haven't solved this problem yet, so hopefully this won't be too terrible. And I'm going to start making those sound effects all the time, by the way, because they amuse me. So in this problem, let's do this by vector analysis, right? So this is going to be vector math. Why didn't those letters come out? What's going on? Is my pen breaking down? I have another one downstairs I have to go get. Vector math. Yeah, I wonder if the battery is dying in this pen. They're itty-bitty batteries. Bar AB rotates at 6 radians per second in the clockwise direction. Use instantaneous center of rotation. No. We're just going to determine the angular velocity of BC. We really should be, in this kind of problem, it wouldn't be surprising that we would ask for the velocity of C. That would be a oh, I'm sorry. My knee just hit the desk. I think that's what... some of my other classes tell me that there's a huge loud noise that happens periodically. I think that's what it is. So if we were going to do the vector math portion of this, what we should do maybe to get out of the way is to write the things that we know. We have omega as a vector, AB that's given, is going to be a negative 6k radians per second. And position vectors we can get relatively easy. We can get R of, and let's say that it's going to be B with respect to A. The position of B with respect to A is going to be 4I. Give him a hat. My pen's not working, and I always feel nervous with my palm touching the screen here. It's a very warm screen. It's very unnerving. And it looks to me like that's going to have positive 4J. And those are inches. And then I'm probably going to want to get C with respect to B. So that instead is going to be 10I plus a negative, and it looks to me like a negative 7. So if I'm going to get the velocity, first I want the velocity of A. So I know that's going to be, oh no, excuse me, the velocity of B. I want the velocity of B, and if I was going to be very precise, I'd say it's the velocity of A plus, let me go stage by stage. Velocity of B with respect to A. So that's the velocity of A plus omega AB crossed with R B with respect to A. But I happen to know that A is pinned, so he's going to be 0. So I will take omega, which is negative 6, and cross it with RB with respect to A. So I multiply it by 4, and then I cross K with I. And then I also, because I've distributed across the position vector, I also do this again 4, but it's going to be K crossed with J. And remember, for a cross product, we go I, J, K right here. And so for my rules, if K crosses into I, that ain't no problem. That's just a regular J. If I cross K into J, that's a negative I. So what I'm left with here is going to be negative times negative. So I got a 24I right here. I got that right from here. That's negative 24 times negative. And then, but over here, it's going to be plus a negative 24J. And if I have any question of that, I could just draw what I suspect, and I don't think that these are correct, by the way. The look of this makes this look like it's 90 degrees, but I don't think it is. So I'm going to move it over here. We know that the velocity of B has to be going down to the right and down, so we know that we got that correct. It's important that you make those kinds of checks as you go along. Now we want the velocity of C. And we take the velocity of B that we now know and add the velocity of C with respect to B. And we could also, we want to stretch this thing out and say it's going to be omega BC, which is actually the thing we were looking for in this problem, crossed with our C with respect to B. So I take it and I can go ahead and write the 24I plus negative 24J, and then I add in omega BC without a hat times 10, and that's going to be my K crossed with I, and yep, I think I got it, yep, and then I go plus omega BC, and now it's going to be negative 24, nope, excuse me, my bad, negative 7, and then K crossed with J. And over here on the left-hand side, what I could do is I can write that what I know, or I believe, I suspect, is that VC as a magnitude is only in the I direction. So maybe sometimes it's better to even write it out like this, VCI plus 0J. So I can solve for the J. In the J direction, 0 is equal to, and maybe I should have, because I usually try to be consistent with this. K crossed with I, we already know that's J, and K crossed with J, we already know that's negative I from up above. So in the J direction, we have 0, we have negative 24, and we have plus omega BC 10. So we can solve and get omega BC is equal to 2.40 radians per second. It's positive, and that means in our sign convention, positive means counterclockwise. He said that in a weird way. Counterclockwise. And that was all that was asked, but we could have now finished up and done in the I direction and said that we had VC now on the left-hand side, 24I, and then plus a, now we could substitute for the omega BC and get the 2.40 times our negative 7 in here, and I believe what we will get, I could have cheated and look on the next page here, or look at my page, but I believe I will get a 50.73 from my other problem, and let's see if that works out here. No. Oh, no, that should have been positive, because that right there and that right there. All right, so I add those together and I get a different answer than I expected. Why, oh why? I did something wrong. Is it that? 10? I feel like I did something right. I think I did everything right. So maybe on my math on the next one is going to be wrong. Let's see. Let's see what happens. Because I did this additional thing here with the Icr method. That's all I did when I solved these right here. But we'll see what happens. It's exciting. So let's see. Let's do this another method. This is going to be the 3-diagram method, as I refer to it. Spelled wrong. And method. So what I would do here first is I'll draw my one diagram. I only need one diagram when it's going to be here. And so this is, we're told this is the omega AB. And this is velocity of B. I need a couple things that I don't have yet. Excuse me. I need the distance. Nope, come back. I need this distance, but they didn't give it to me. So that's 4 by 4. So that's going to be, I guess I'll call it length AB is going to be the square root of 4 squared plus 4 squared. I heard a doink. Is that doink a question? A comment? Ooh, we got a couple chats. Couple chat things. I'll leave and come back. Are you going to explicitly ask us to use certain methods when answering problems? I will. And so will Dr. Orlip, but I'm not sure about anybody else. Dr. Orlip and I had that discussion at one point, and he was like, "Oh, yeah, hey, well, we could ask them to do it this way and to do it that way." And I'm like, okay, that's cool. And so just be able to do it. 5.657. Because it isn't about getting the answer. It's about demonstrating that you understand how to approach problems and how that you're able to solve a problem when presented with it with a particular method of applying things. So that's a rationale, right? We also would want the angle here, but we could see that the angle is going to be 45 degrees and going, let's see, this way, right here, right? Now I want to go and so I could find what VB is just going to be omega AB times LAB. And I just wrote inches per second, and that was silly. Inches, right? So now we want to go 6 times 5.657, and we should end up with an answer of 33.94 inches per second. And then now we go through the actual 3-diagram method, because what we're doing here is we're making a representation of link BC flying through space and spinning. And we might need to do some geometry here to keep this thing straight. I'll go ahead and let me do some of that geometry. All right, so if we want to find this angle, I'll call him theta C right here. Theta C is going to be the inverse tangent of, what's that, 7 over 10? Inverse tangent to 7 over 10 is 34.99 degrees. So if you were going to do the rest of the if you're going to do the rest of the geometry here, no, that's all you need. You don't need anything else. Sorry. You also need the length. So the length of BC. Did I ever get the length of BC? It's going to be 10, the square root, or let me see, I got to find a good place. I'll put it up here. Length of BC is square root of 7 squared plus 10 squared, and that ends up equaling 12.21. And so now we could go back and take a look at some of these other things that we want to put onto there. So we're going to have the velocity of B is actually going to look a little bit different. It's going to look like this right here. It's going to be the velocity of B. And that's the known, and then we could know that C has to move along that line. So what we're going to write out and try to find the velocity of C, it's going to be equal to the velocity of B, which we use as the reference, plus the velocity of C with respect to B right here. So we apply the velocity of B at both places, and then we pin it. We use a purple pin. We pin it at the reference point, and then we have to decide which way is it going to rotate. Is it going to rotate clockwise or counterclockwise? Well, we know that the line of velocity has to be perpendicular to this link in this pinned arrangement right here. So just by logic, if VB, as we've applied it here on the bottom, is going downwards in the second diagram, but in the left diagram has to be completely straight, this one has to be going upwards. So this has to be the VC with respect to B. Therefore, omega BC has to be going in the counterclockwise direction. And here is a good time and moment to go in here and make sure that we're looking at these angles, and that we know that that's theta C is right there, that this too is theta C right in there, so that we could break it up. And then as a strategy, we know that VC has to be 0 in the y direction. So that's the one to go to first in the 3-diagram method. So we go the wider and wider. Wider is going to be 0 equals, and then we might have wanted to draw in these here, and even though it doesn't look like it, that's 45 degrees. So, and in the y direction, it's negative. So it's this VB negative, or 33.94 negative, but only the vertical part of it. So as I've drawn the angle, that would be the sine of that angle downwards. And then I would add, now the y direction on the third diagram is upwards. So we go plus, and that VCB, we know the magnitude. By the way, I have an arrow there, so I don't need a hat on top of him. This is just the magnitude. This is going to be BC times the length of BC. So we go omega BC, and the length was up there, 12.21, and then, but this is going to be the cosine of 34.99, pretty close to being 35. And so now we could solve for omega BC, and if we solve for omega BC, we go 33.94. Actually, I should probably have that down in there somewhere. 33.94. It was not in there. Divided by, no. times sine of 45, right? Divided by 12.21 and divided by 34, the cosine of 34 point right here, divide, and we get 2.399 because radians per second, and we found that it was counterclockwise up here, so we have counterclockwise, so we get the correct answer. And that 22.399 is different from here because of old round off error when taking square roots and whatnot. And then if we weren't asked for it, but let's check what this x direction is going to be, because it's right here and we got it in front of us, and that's often the thing I would probably ask personally. And I'd write down here, because they're not, remember, I'm working through components right now, so these are not vectors, so I don't put a hat on that particular guy. I'm getting just the magnitude, and I'm looking in the x direction. And I see that we have the 33.94 again, but on the horizontal direction, and that happens to be positive in the figure. And we'll take the cosine of 45, because it's the adjacent. And then we'll also, this one in the right diagram is also in the positive horizontal direction. And we know it's omega, it's what we just found out. I'll just purposefully stick with the number my calculator came up with here, even though I know it's 2.4. Times 12.21, that's the LBC. And now we want the sine of 34.99. And if I work that out, I get 33.94, 45 cosine times 2.399, 12.21 times, and then 34.99. It's interesting there that they said that they're similar numbers. All right, sine times, add them together, I get 40.80 inches per second, and it's positive, so it's to the right. But you could just look at this and you could see that it had to be to the right because of the arrows up in here. So that's the 3-diagram method. And then lastly, we could do this by using the Icr method. And so here, I start out with really the same thing. I could really just take what I've done right here and move it down to over here, right? But we draw this thing in the 45 degrees, come up here, find out, we had to find out the length of the thing again, right? So we could get VB, and so we happen to know that VB was equal to 33.94 inches per second. You know, we had to go through the process of getting that length into there. We also would probably need to get the, we don't necessarily need to get the length of that. Maybe we do. Yes, yeah, we do. Okay, so now what we want to do is do the Icr, and I kind of recommend that you redraw this thing for yourself instead of trying to draw on the diagram over here, because it could get kind of messy depending on your what you're dealing with here. But like what I will often do, just so you know, full disclosure, is I will sketch onto the diagram itself, but then I will redraw the diagram so I can get all the angles that I want. So just as a quick sketch on top of the diagram, just to get an idea of whereabouts the Icr is going to be, I will draw, this is the direction that I know that the velocity is going to go right here. And when it's a linkage like this, we often can just go ahead and just extrapolate, just draw a line right through the linkage, because that is the line that's perpendicular to the velocity. When it's this guy right here, we know this guy is traveling horizontally, so his line is up here. So I can tell my Icr is way up here somewhere. So I want to, when I redraw this linkage, I really want to, I want to give myself some room up above. And so I'm going to draw, and I'm taking I have my an old driver's license right here. You could take your ID card. Whoops. And that's one of the problems with this tablet thing is that it often is shifty if you get your fingers on it. All right, so I can take that driver's license. What I do is I kind of line it up with the figure, and then I slide it without rotating it so I have the correct angle. And then I can draw it upwards from right here. And I give myself enough room? Almost. Right, so right here is the ICR. And I want to start looking at some angles. I want to start breaking some angles down. I find an easy way to do it is to break it up into, wherever I can, into right triangles. Another method of doing it, of course, sometimes we want to do law of sines. And is that what I did? I didn't do law of sines or law of cosines, but I could have tried to do that. What I did instead was I took a look at the geometry that was provided to me right here, and I knew that from right over here to right over here, this was going to be 7 inches, right? And I knew that this right here is going to be 45, right? Because it's the same thing as this angle right here, which was 45 because it was 4 by 4. And I already knew this angle right here that I called phi. I calculated that there by the inverse tangent, right, if you recall, of 7 over 10. And got 34.99 degrees. So what I need to do here is I could get this length right in there. And I decided to keep things, to keep track of things. I created a point I called E. And then so I could figure out what my length is right here. So this is going to be, this is B, C. I want, let me think here. And that length of, okay, so that length of BE is already provided to me, and the length of BE is going to be 10, right? That's this distance right there, 10. And I know the angle. Okay, so what I can do, and every one of these problems is a little bit different, not every one of them, but many of them are different in terms of the approach we might want to get for the geometry. So we do have to think. It's definitely an issue I found with students in dynamics quite often, is you have been quasi-trained up to this point to look for and memorize methods. You want to try to break yourself from that, as you really have to think your way through things in many different fields and many different areas. And I'm not picking on you. I'm telling you I've had the same issue in my life. I had to do it too, and I still find myself trying to look for ways to methods, to repeatable methods. But anyway, I'm going to take the cut we'll use, because we know this line, and I want to get this guy right here, which is RB with respect to ICR. We will take and we'll divide by the cosine of that 45. So 10 divided by the cosine of 45 should give us the length, 14.14. And then if I want to get the C with respect to ICR, because this is a 45 degree angle right here, or it should be, that side BE should equal E to the ICR. So the R C with respect to ICR, which we actually won't need, by the way, is going to be equal to our 14. I think this word, I made a mistake. No, it's going to be 7 plus 14.14. All right, hopefully. I hope so. and so that should be 21.14. Let me think again, double check everything that I got here. I believe that's going to be correct, but that's I'm looking at the thing I got later into there and later at the bottom of the page. I'm like, I'm still suspicious. But anyway, so we got velocity of B, right? So now all we need to do is, and we know that the velocity of B is going to be something like this right there in our diagram. Boy, this thing sure does look like it's not. There you go. It's going to be like there. It's not in line with that. That means we have an omega BC, and so we could find omega BC by taking the velocity of B and dividing it by the RB with respect to ICR. So we go 33.94 divided by 14.14 and 33.94 divided by 14.14. We get 2.4. Yay! That's the answer. And we saw from this ICR that it was counterclockwise. Now, if we wanted to go further, and the question didn't ask for it, but actually find what the velocity of C is going to be, we would take the velocity of C is going to be equal to omega BC times R C with respect to ICR. And hopefully, if we go 2.400 times 21.14, I'm not feeling good about this. Nope. I just messed the thing up. I just messed my calculator up. 2.4. I got the wrong answer. Damn you, damn you, damn you. So what did I do wrong? I must have my ICR distance. This distance must somehow be wrong. Dang you. Oh, that's it. This is just 10. What the hell was I thinking? Right? Because this length is 10. So this length is 10. So that should be 10. So that should just be 17. It's the geometry that gets you, you know? So 17 times 2.4 is 40.8. Whew, 40.8. Dang you. Yay. So here we go. 3 different methods to calculate the same thing. And we did 3 problems. And how much time did that take us? That took us, well, give and take, what time did we start, right? We started at 1:30. I don't think it took us the entire time, but we had some other things in there. But they should have taken us about less than 15 minutes each, right around 15 minutes each to do those problems. We can go back, we can look at the video, we can see how long it actually took us. Is there any questions? Let's see. We got some people here, right? There's people. Let's see how many people we got. Yeah, we got the same 4 people. Thank you for participating here. Thank you for being here. Let's see. Let's go move this thing over the side so we don't have to see that cascading nonsense. Is there any questions? Comments? We can play some more sounds. The sounds can help things right here. Oh. I don't like that one. There you go. No? All right. Well, let's do some acceleration stuff then. We can continue with this same problem. Actually, I have it later on as an acceleration problem here, where it's the same problem, but now we've extended it to ask what is the acceleration of the oh, look at this. I'm saying I have a slightly off thingy. Let's see. Let me double check. Yeah. Huh. Wonder why. Anyway, we do a velocity analysis first of this piece, and we can assume that we got the omega BC is going to be equal to 2.400 radians per second squared, and going that a ways. So if I do an acceleration analysis of first, I have to step through the parts, and I take a look, and I'm going to have two kinds of accelerations going to take place at B. I'm going to have tangential, and so technically this is the acceleration of B with respect to A, tangential, and I'll also have a normal acceleration of B with respect to A in the normal direction. And the magnitudes of those are going to be alpha AB times RB with respect to A. And I could do this in a vector method, by the way, but I'm going to do a 3-diagram method. So we were given... Oh, wait a minute. This is an interesting problem. This is a difficult problem here. Okay. So maybe I'm going to pick a different problem. Okay. So I'm certain it's not a difficult problem, but it's a catchy problem, because the acceleration, what is the acceleration of slider Z? What acceleration is needed here to get the acceleration of C? It's not that we couldn't do the problem. It's just that I think it'd be better to do a more straightforward problem than to tackle this one right here. It's just that this is a kind of a niche type of dealio, where you would have to try to you have two equations and two unknowns at the end of the thing in order to try to get the thing to solve. And I think that's probably where I wrote down at the bottom of mine. It was like, hey, I'm slightly off from what the posted solution is. But so let me go to a different acceleration problem. Let me take a look and see what I have to choose from. I will do a slider crank and so I'll do this guy up here. All right, so we're told here that this has a constant angular velocity. Let's see which one is OQ. That's a weird naming, and it's counterclockwise. So it's going with an omega OQ, if you will, of 2 radians per second, counterclockwise, and constantly. And we want to know what the angular acceleration of PQ is. And then also I probably wanted to know what the acceleration of P would be. That's probably what I would have asked. If we do, and I do an ICR of this, because we have to do a velocity analysis first of this piece. And so if I do an ICR, I do a quick and dirty one of this piece right here. First we find the velocity of Q is going to be omega OQ times L OQ, and fortunately they gave us the length instead of just those coordinates there, and so that's 200 millimeters, so we get 400 millimeters per second. If we do the ICR of this there, where's my driver's license here? My old driver's license. I don't know why I keep these. It's interesting, right? So if I do a ICR of this, is very similar to what we just did, by the way. No, come back. And this theta here is 60. It sure doesn't look like it's 60. So I think if I were to draw it upwards, like, that 60 is probably more like that right there, probably. Right? So, I don't know. I don't want to draw it too high right here. Yeah, this is going to give me problems. Oh, come on. What's bad here is that they didn't give us the they didn't draw this thing like really great. But let's see. It's just that my diagram is now getting in the way of the words that I've already written. I kind of get annoyed by that. Come on. Okay, I'll do it freehand. It doesn't like, so this stuff is in the way, so I'm going to get rid of it. But we know that the answer was 400. And taking that IC, with that length right there, and this is 60 degrees right here, and we could get what this distance is going to be. Do I do that one first? Yeah. Where'd you go? Okay, yep. So what I did is, first off, I found, based on the geometry here, I used the law of sine. Yeah, I used the law of sines to find this beta, what I called beta, right in here. And I said that if 400 divided by the sine of 60, right there, right? Because that's 60 right here. It's opposite of the 400. It's going to be 200 divided by the sine of beta. And therefore, beta is going to be equal to 25.66 degrees. And then I could also find what I call up here. I went to decide. I said go phi is going to be 180 minus 60 minus 25.66, and it's a little annoying that it's close to 90 degrees. That makes the diagram a little bit more difficult to deal with, because it looks like it starts to make it look like 90 degrees, but it's not. And then if I want to get the length between OP here, I could use the law of sines again, and I go 400 divided by the sine of 60, and then I will go is going to be equal to OP divided by the sine of 94.34, and I will find that OP, that length, is going to be 460.56 millimeters. And now, now that I have this length right here, it's not that difficult to find this length right here, which is going to be, which I actually don't need, to tell you the truth, but that's going to be RP with respect to ICR. What I really need is this length right here. That's going to be RQ with respect to ICR. All right. So how did I do that? I said where did I go? I know how to do it. Let's see. I'm trying to see what I did. Oh, okay, I did. What I do is I could go RQ with respect to ICR, because I wrote it really small. That's why I was looking at the thing. And so I'm going to get this all hypotenuse guy right in here, and and then I'm going to subtract out the 200 from it, right? So I'm going to get the entire thing. You could say I'm going from O to ICR, but then I'm going to subtract out O to Q. So I take my 460.56 and divide it by the cosine, of 60. but then I subtract out 200. And I'm left with a value of 721 point, what did I write? I can't read that. 1211. It's good. Millimeters. And now I want to get my, so I already had, this guy was 400. So I find my omega PQ. It's going to be VQ divided by RQ divided by ICR. And so that's going to end up being 400 divided by 721.1. And we're left with 0.5547 radians per second. Oh, and by the way, that's going to be that way, counterclockwise. Wait, I just messed it up. It's going to be, this thing was counterclockwise, so it's going that way. So this must be going clockwise. That's omega PQ. Yeah. So that means that actually this the P is going has a velocity to the left. All right. So now I do my acceleration analysis. And so this is really, in an exam question, this is where it would really start, probably, because I probably would have given the angular velocity so that we could concentrate instead on the acceleration part in the problem. And so in this linkage OQ, we would only have a normal acceleration. So the acceleration of Q would be entirely the acceleration of Q with respect to O in the normal direction. So it's going to be omega OQ squared length of OQ, or as given, that's going to be 2 squared times 200, and that ends up being 800. Could do that in my head. Millimeters per second squared. All right. And now, because we are running out of space here, let's make another slide. And so I will keep this. Keep. And apparently computer is not happy. I just want to check you guys are still here. Let's see. Boom. Still with us? Oh, Phil's here. Hey, Phil. And yeah, what I want. Okay, I wanted to give myself some more space. So click right here. Computer is slowing down. There's too many things going on. I have too many apps going on at the same time. It's probably my let's see, get rid of slicer. Let's see here. You can see my, this is me remoting into my computer at work. And you can see, isn't that kind of a cool little thingy doohickey right there? You can see that while we're right here. I was going to show this anyway. See, there we go. There's acceleration and velocity being put on top of this mechanism there. I'm 3D printing this right here. I got it, all the gears and I got the stuff laid out. I'm having trouble 3D printing that stupid red piece right here because my, silly me wants to make all my make all my parts that are in reality the same color as the parts in my model. And so see, I'm not really, this isn't getting down either. Let's see. Okay. Yeah. What happened here? Did it discard this stuff? I must have discarded all the stuff I just wrote. Well, I know what it is. So let me come back into it. Yeah, so the red PLA that I have doesn't work well. And it keeps failing. So that's what my life is about right now. So let me I just did this, but let me I'll duplicate this slide. And back here, get rid of that. All right. So here's where I'm doing my acceleration analysis with the stuff that I've previously had. And I'm going to do a 3-diagram method here. And if I had more time, I would do this using vector math too. Sometimes the vector math is definitely can be a shorter process, can be quicker. But I think this one gives you more insight into what's taking place. What we had up here in terms of the accelerations, we knew, whoops, sorry. We had an acceleration right here. This was our, this is the wrong problem. What the hell is going on here? I know what happened now. I'm sorry. When we got out of that, we went to a different slide because my computer was slowing down. There we go. All right, so we're back on track. But I wanted this. Okay. All right, so yeah, it confused me. They're very similar problems. Okay. Been better if I drew these the same. I know, I'm being picky. Close enough. Okay, so we know that the acceleration is coming down right here. Here's an acceleration that we know. That is going to be AQ. And the acceleration of P has to be along this line. Right? It can't go up and down. It has to be along that line. So we're going to write down the acceleration of P is going to be equal to the acceleration of Q that we know, plus the two parts. The acceleration of P with respect to Q tangentially, plus acceleration of P with respect to Q, and I really need more room here. I'll drop it down a little bit. Acceleration of P with respect to Q tangential plus acceleration of P with respect to Q in the normal. And these are vectors. And so when drawing this out right here, we're taking the thing that we know as the translation, and we're pinning it up here above at the reference. And now this thing is going to have first it's going to have an acceleration coming this way. Let's see, I'll get rid of that little hat. And that's going to be the acceleration of P with respect to Q in the normal direction, going towards the center of the pivot. And then it's going to have a acceleration, tangential acceleration, that's in this line right here, but we don't necessarily know what direction it's going to go. When in doubt, I choose an alpha that's going to be counterclockwise, which is considered the positive direction. So I'm going to go in this positive direction. And so that right there is going to be the acceleration of P with respect to Q in the tangential direction. It's a good idea at this point, or at a couple different points right here, to go ahead and put in what the angles are going to be, right? So this angle that I have right here, even though it doesn't look like it, is 60 degrees. So I can put that in there. and maybe I can move him a little bit. And that's going to be 60 degrees. And so over here, though, this angle is going to be the one that we previously got, that beta, right? So that angle is the 25.66 degrees. And the same thing is going to be true right here. I'll just put beta. It's right in there. So now that we have all of that arranged, we can write out the stuff in the x direction, the y direction. The y direction is the one, once again, very similar to the velocity analysis that we did of that other linkage. Going in the y direction is going to be a good strategy because we have 0 here on the left-hand side. So the component of the AP is 0 in the y direction. Then we go to AQ, it's going to be downwards, negative, right? And we found for AQ, we found that it was 800. So we take 800, and it's going to be only the y component of it. So it's going to be the sine of 60 degrees. And then we're going to go to the next one. That's going to be the tangential. This is the one that we guessed. And we guessed it's going to be in the positive direction right here because the alpha, so that's plus. We take the alpha PQ, and then we take the length of this, so that's 400. But here's the important thing, don't forget this. We need to take it only in the vertical direction. So where this is, we have a beta right there, and in the beta, we're going to have a cosine of that beta, which is 25.66. And then marching on to the next one, we have PQ in the normal direction, and that too is going to be in the vertical component here. So that's why it's positive. And then we're going to have the angular velocity, omega, of the PQ, which is something we found from right here. 0.55, my memory's bad, 47 squared times the length, right, which is 400. And then got to remember, only the vertical component, which ends up being the sine of 25.66. And if we do all of that, we're able to find the PQ as being a 1.774 radians per second squared. And we get a positive value, so we did choose this correctly. A lot of times I will write guess right up in here. And this matches what the solution manual or the book, the back of the book provided. And this is a Benson and Fowler, I think, problem. And we didn't ask for it, but in the x direction, it allows us to be able to get what AP is going to be in the x direction, which is completely in the x direction. And so looking through this, we march through again, and in our diagram we see that AQ is completely horizontal in the negative direction. Not completely horizontal, it's horizontal. And we would take the cosine now of 60. And now we go to the tangential one right here, and we see that that's going to be in the positive direction. And that's going to be alpha times the L, but that's 1.774, we just figured out, times our 400. And but we're going to take now the sine, because it's like, you know, right here, going the opposite of the beta angle right there, 25.66. And then, okay, well, we go to the next one, the normal, and we see that it's actually in the negative direction. So we have a negative, and that's going to be omega squared. So that's the 0.5547 squared times 400 times the cosine of 25.66 degrees. And we find out that MAP is a negative 203.8 millimeters per second squared. So AP as a vector answer is 204 millimeters per second squared with an arrow. Ta-da! And I can't, boy, my computer is really messing up right here. I'm not even sure you guys are there anymore. That's how messed the thing up. Let's keep this and see if there's any questions. I see a chat. Hey, you have more fans than I do today. Oh, that's cool. I'm glad to hear it. Well, I'm sorry that you don't have more fans. I wanted you to have more fans. Where did you get the 0.554 value from? Good question. All right. That came up from right here. I did a velocity analysis first. I'm not sure you joined us later, maybe, or I did an ICR first. Chances are, when I ask an acceleration question, it's just my preference is to try to split apart the kind of questions that I ask. So I like to ask 4 questions or 3 or 4 questions. So one of the questions that I might ask is just to find the angular velocity or find a velocity. And then when I ask for the acceleration question, I probably will give the solution. I'll probably give what the angular velocity is, but I found it by using the velocity analysis and doing an ICR. How's everybody else? What's up? Anybody got questions? Let's see. We got time left. Want to do? We could do a 4-bar one. Maybe you're not familiar with what I mean by a 4-bar. But you could make the point, aside from maybe just having a bar that's like flying through the air or something, or just a single bar that you're using for rigid body motion, that you could really break things down into 2 kinds of mechanisms that we'd use for rigid body motion. This one's called a 4-bar. And it's, even though you only see 3 bars, they mean the ground. Like if you were to connect the linkage at the bottom, that would be the 4th bar on the thing. It's just the thing that they call it. And this one, like here, we call this a crank slider or a slider crank, right? And it's like an engine, like that you might have. So you'll notice, like, you could call, like, this problem right here, where I did this with this is a slider crank. It was actually a crank slider. It's called a crank slider because you're manipulating the crank, and you're seeing, and then you would find the information about the slider. If you did the other way, where you make the slider the input and you want to find out the crank, you call it a slider crank. I know, exciting. This one actually would be considered a 4-bar, even though it's got a roller thing on it, because these at this moment act as instantaneous centers right here. So this actually is sort of like a 4-bar mechanism, except you just don't see the bars right here. And then the ground becomes right here. So like as you're trying to find what the behavior of this is, you would call that a 4-bar. And then, here's a classic 4-bar type of problem is right here. So here's the crank, and then this is the coupler right here, and this is the rocker, and this is considered, it's called the ground right here. But that's the kind of problems it might have. Like right here, this is also a 4-bar. It's kind of hidden right here. It's a 4-bar with a little extender thingy on it right here, right? But if this is still a 4-bar mechanism right here. So you can, just to organize thoughts and to communicate that we would have this. So we could find the acceleration of this, and this one's a little bit more complicated because it does have input input angular acceleration. So it's a little bit more, there's a little bit more work than you could be expected to do, I think, maybe. I don't know. Depends. But so just word of caution here, this is a difficult problem. And we definitely will be going into overtime to be able to work on the thing, but I don't mind. you guys can stick around, you can leave, it'll get recorded and uploaded, and I will share the information with the other professors. So just so you know, whether you have some place to be, like maybe the kitchen. Sorry, it was kind of funny in my brain, right? So if I'm going to do an analysis of these, I almost inevitably have to do a velocity analysis first, and I will try to make this look like the thingy. I should really be using my driver's license again for the motion of this, but with the inputs that were provided, this is going to have a velocity here. We know this is the velocity of B right here, and I'll write up here the velocity of B as a value is going to be omega AB, so 4 times length 2, I could do that 8 meters per second, and drawing out the ICR stuff of this, we'd come about, and there's the line that's perpendicular to there. There's also, we know that this one's pinned, so it has to be working on a line, and once again, unfortunately, this is not a 90-degree angle, so you have to be careful. Its velocity does not line up with BC, even though it looks like it could. It's going to draw a line and extend, and it's going to land right there, and that's where the ICR is going to be. Got to be careful with some of these. They are a little bit challenging to see. So really, when I'm doing the ICR, I should probably just isolate these right here. And then we would see that the velocity of C would be right here. And we could see that the omega of BC is right there. So we could find with these distances right here. I wrote all kinds of muckety muck and googly about. I do need a couple different geometry things, so maybe I should write that over to the side because they didn't give us the lengths of BC or the length of CD or of the angles, although we can infer what the angle is of BC pretty easily. You could see that that's just going to be a 45-degree angle, right? Because you're going up 1, and based on this going over 2 and over 1 and over 2, you could also see that this right here is also 1. So you know that this is going to be 45 degrees right here. But now if we want to get the length, what did I write? I did write, I'll go length BC is square root of 1 squared plus 1 squared. You should even just be able to look at that, right, and be able to go, yes, that's 1.414 2 if you want another sig fig. And then we go to the length of CD, and that's the square root of 2 squared plus 1 squared, and that ends up being 2.236 meters. And if we wanted to get this angle right here, I'll call him phi. Did I call him phi here? Yeah, maybe. Sometimes I'll call that theta D, right? Because D, it's the point that inside of D. But I guess I decided to change it. All right, go on. Why not? And so take the inverse tangent of 1 over 2, and we get 26.57 degrees. All right. So based on this right here, we notice that this right here has to have the same, you know, we're looking at this and we're going, oh, right, these are parallel lines and this is drawn through there. So that has to have the same angle right here. So did I have to do law of sines for any of these things to get that? No, because we know that this right here is 2, right? So what we could do to find the R of, let me double check what I'm doing here. Yeah, the R of B with respect to ICR is going to be equal to this big leg right here minus this distance. And so that ends up being, where'd you go? Oh, yeah. 2 divided by the tangent of 26.57 minus 1, right? It's because this is length of this part right there is just 1 right into there. And that ends up being 3. That's interesting, right? But it is true. So we get 3 in between there. So we can get the omega BC by taking the velocity of B and dividing it by the RB ICR, and that ends up being 8 divided by 3, or 2.667 radians per second, and that looks like it's counterclockwise. Now we are armed and dangerous. No, not quite yet. We also need to find the omega of the other bar, right? So we know that C has to go upwards of here. So let's get velocity of C, but we do need this length right here. We need this RC with respect to ICR. And what do I need to do to get that? Let's see, I played a little bit of a game. Yeah, I took and I found this whole length right to here, and then I subtracted out the length that I found right here. So I said that I did a similar thing here, but I took 2, and now I found the hypotenuse by getting the sine of 26.57. Nope, that's not what I'm doing right here. RC with respect to ICR. And then I subtract it out. So that's going to give me this whole length right in here. And then I subtracted out my 2.236. And I was able to get... this actually turns out to be a kind of a silly answer, but that's right. 2.736 meters. So now I can find my velocity of C. And that's going to be my omega BC, right? My omega BC times my RC with respect to ICR. And that goes to 2.667 times 2.736. Wait a minute. Whoa. Yeah, I guess I'm going to believe that. Sure. Yeah. So that comes out to 5.9628 meters per second. And then now I want to get go back to this other linkage right here, that linkage DC. And so we could also say that the velocity of C is going to be omega DC times the length of CD. I like to go in order right here. I don't know why I went to CD. So we could find omega CD is going to be equal to VC over LCD. So we get this 5.9628. And we divide it by the length right here, right? LCD, or 2.236. And I swear something is wrong now. Let me see. Because I say I get 2.667, which doesn't make sense to me. 2.667. No. So, excuse me while I look at this thing. I solved this the other day, and so I'm trying to decide. I have 2.667, and I multiplied by 2.736, and I should have gotten is an in-between number. 7.297 And then if I divide by 2.236, I get 3.263. I'm a little concerned about how I'm going off the rails here, because I know that I did get the correct answer the other day. And this is not what the path that I'm leading down that's going to get me there. But I did get it. All right. So anyway, this is going to be a really long problem. That's going to really confound people. I'm a little concerned that's going to mess people up. But I could go to the heart of it, to the right thing. And like I had mentioned, this is like more challenging than most exam problems can be, because it does take a long time to do. But we got to this stage right here, and hopefully these are the correct values. 8/3. It's probably the lengths, if there's anything wrong with this. 2.667 and 2.236. Yeah, that's what happened right here. Okay, let me go back. I'm sorry. Sorry. Don't be mad. It's tough to talk and think and do this at the same time. We got C with respect to ICR. Okay, that's what I did wrong. I'm sorry, I wrote that wrong. This ends up being, because of symmetry. It's because of symmetry. So that's where I messed up. I apologize. As I'm writing through the thing, I misinterpreted my own handwriting. 2.236. Okay, back on track. This ends up being 5.963. And then we have 5.963. But then we take the LCD, and that ends up being, because it ends up being 2.236, we get the same thing. All right, so that's what I was hoping and what I thought before, and I didn't trust myself, so we looked under the thing, and so maybe the thing to learn is to trust yourself. But the omega here for this one is going to be clockwise, because you could tell from the VC is going upwards right there. All right, so here now, after doing this is where the acceleration analysis begins. So let me add in another page here. I want to keep it. Add in. Come on. Computer doesn't like it. Look, it says not responding. How about you guys? Are you guys responding? How many people I lose? I lost one. All right. Is it Phil? Did I lose Phil? No, I still got Phil. No, I lost another one. All right, I lost two. All right. Sorry about this, guys. This is maybe I should have picked an easier problem, but sorry. Let's see. Copy this one over. Cut it back in. Paste it. And now the acceleration analysis begins at this one. But this is a hard problem because it's got a number of things to figure out. One of the very first things that we would do in acceleration analysis, if we'd already had the velocity analysis, was go to the first link, and that's stationary, right? Or not stationary, but is given, and get the normal and tangential accelerations. So this would be AB tangential and AB normal. AB tangential is going to be alpha AB times LAB. Or we were given that it's going to be, oh, wait a minute. They told us that it was negative. So they've drawn it positive, but it's actually negative. So those tricky bastards. And I'll move this guy over here because he's in the way. So anyway, he's a -6. So he's a 6 times a 2, and that's 12 meters per second squared. And then for the acceleration in the normal direction, we get omega AB squared LAB. So omega is 4 squared times 2. 4, so that should be 32, right? 32 meters per second squared. It doesn't hurt us to to skip over BC, which is the complicated one, to go over to DC, CD, set him up, and maybe just write out the things that we're going to need to do. We don't know what direction the alpha is going to go on this, right? So I'm going to guess it's going to be in the counterclockwise direction of CD. And maybe I'll even write guess next to it. But we do know the direction of the normal. So the A of C in the normal direction is going to be omega CD squared LCD. And we just found out omega CD was 2.667 squared. And we found previously that CD, its length was 2.236. So 2.236. So we can actually find our value. And did I write that out somewhere? Hopefully I did. It should be like, I think so. Looking down. Where'd you go? 15.90 meters per second squared. And I did draw this one out, right? So I did make the angular velocity here, so we could write that the AC in the tangential direction, that's going to be AC in the tangential direction is going to be alpha CD times 2.236, and we don't know anything further in there. But those are some things that we could have done that we know. Then we move on to the the most difficult of them is the BC. And here I do my 3 diagram method. And I fully know B, so I'll use that as the reference to this thing, right? So I have that down and that over, right? And I could probably just keep things easier, call them by the X and the Y, right? Because it's nice that they show up in the X and the Y direction. A, B, X. It's useful to us. So I'll write A, B, X. Because I don't really want to keep them calling them tangent and normal, because the tangent and normal is all about the other diagram. And now we have, let's, over here at this point at C, let's keep, and this is what makes it complicated here, let's keep the directions as we that we have, right? So because we happen to know this direction, we happen to know this AC, and I guess I'll keep calling him N because I don't have a better name for him, an ACT. And so what we're trying to do is we really are trying to find what the acceleration of C is going to be. So we write the acceleration of C. It's going to be acceleration of B, which is what we know, plus the acceleration of C with respect to B in the tangential direction, plus acceleration of C with respect to B in the normal direction. And I guess I'll put this on here. So the B is the one that gets pinned in the rotational, or the one that represents the rotational side. So let me put the X and the Y right here. And we have AB, X, Y, AB, X, AB, Y. I really picked a hard problem, by the way. And then over here on this one right here, we have this is going to be the AC, with respect to B, normal. And then we don't know this direction here, but we can assume counterclockwise alpha. That's going to be alpha CD. And so if we assume counterclockwise, that makes the alpha C with respect to B tangentially go that direction. We should probably get some angles involved in this, unfortunately. So here is the angle that we calculated up here. I guess it's a theta D is what I ended up calling it. So here's theta D. And so right here will be theta D. And then this guy right here is 45 degrees. So that makes this a little easier right here. This is 45. And this is 45 degrees right in there. I say a little easier, but this is definitely a difficult problem. Now we can proceed and we can go the X direction and the Y direction. What's going to happen is we don't have the benefit that we had in a lot of other problems where things aligned with the X and Y direction. So we have a lot more stuff going around. We can't pick one that's going to be we can't pick one that's going to be easy to us, right? So we have to we'll just methodically go through here, and it is a pain in the ass. I totally agree. But let's take a look at the X direction. So we are focusing in on point C, and in the X direction at point C, we're going to have, let's start with the tangential direction. It's going to be negative, right? And I'm going to go all the way over to the left over here, so I could try to fit on one line, but I'll probably have to go to another page. In the tangential direction of C, we have alpha CD times 2.236, and then but we need to do it only in the X direction, so that's going to be the sine of my theta D. And my theta D was 26.57. And then still on the left-hand side, we have a component for the normal direction of C, but that's going to be positive right here, and it's going to be, we have the value up here, 15.90, and now that's going to be the cosine of 26.57. Then we move on to the next part, to the right-hand side, and we find for this one we have ABX, and that's it totally, right? So in the ABX is going to be the 32. Do I have that right? Yep. And it's going to be negative 32. And then moving on to the tangential part right here, and we don't know the tangential part right here. So that's going to be alpha of CD times our LCB, right, which we got previously as 1.414. So, and as drawn, I'm going in the X direction is going to be in the positive direction. So I go plus CD 1.414, and it's going to be, and as I've drawn the angle there, the cosine of 45 degrees. And then I also want to get the normal direction. Now, the normal direction, we could actually find this value, because that's going to be the omega CD squared times L BC, and I messed up right here some point. I messed up the naming of these things. Because this guy right here is going to be BC. That would have been really bad. It probably is really bad. Oh, come on. What are you doing? Go away. Why are you doing that? Damn it. BC. Did I miss it anywhere else here? BC. Yeah, okay. All right, so this guy right here, we found that omega BC on the previous part. We found him up here. 2.667. It's actually the same as the other guy. 2.667 squared, and that length we found to be 1.414. All right, so I actually wrote down the value of this somewhere. Oh, come on. And where'd you go? Okay, yeah, it's 10.056. 10.056 meters per second squared. So I'll back over to here. We take a look at this in the x direction, and that becomes positive as the arrow is drawn. 10.056, and now from the way my angles are drawn, that ends up being the sine of 45. Well, that doesn't matter. So what I have right here is one equation and two unknowns. I have alpha CD and alpha BC. And I personally, I reduced this down so it was just into two variables and a constant that you would have, right? And I want to double check. Yeah. What you end up finding, actually, kind of interestingly enough, is that they both of those, what's in front of BC and what's in front of CD, ends up being the same thing. Okay, but anyway, we get the y direction, and we proceed and do the same thing. Like I said, this is sort of a pain. But in the y direction now, we're also going to have a negative CD. But one of the interesting things is if you pick the angles the right way, right, as the angles I've shown right here, one of the reasons why I decided to keep these angles the same is because I can write all this out, and the sines just turn to the cosines, and the cosines just turn to the sines. But you still have to watch out for the plus or minuses as you go through here. So what you can, once you look at this, you can just start marching through and go and look at this thing, and you go, okay, plus 15.90. But it's good to like go back and look as you're going through. But I just messed up because I was talking. This needs to be negative because as you see drawn right here, in the this is the normal part right here. I did the tangential part right here, this part, and that's negative. And now I'm doing the normal part, and that's negative 15.9. But now it's going to be the sine of my 26.57. And then in the y direction here, this is also negative, but we already have that value up above as 12. That's up here. And okay, now we go over to the tangential part right here, and that's going to be negative, and that's alpha BC, and also times 1.414, the length of this. But now it's going to be the sine of 45. And then lastly, we have in the normal direction up above, the y component, that one's going to be positive of 10.056. And now cosine of 45. So now we have a second equation with two unknowns. And we can simultaneously solve them. And when we do, we get these values right here. And it turns out that they are both counterclockwise. So I was lucky when I chose them to be both counterclockwise. I could do the math as you want, a little bit further and work the thing out. But it's the process. I wanted to show a really complicated one where we haven't had more, what do you want to say? We didn't have as many, some simplifications that we normally have had in problems for homework. And for most tests, you really want to have something that doesn't require somebody to do, this amount of work, in my opinion. And my computer is all bogged down now. It needs to have a reset. And I lost everybody but Grace Wood, and Phil. Oh, wow. So maybe this wasn't the best idea to make this particular problem, but it seemed like a good idea at the time. Is there any question? Grace, Phil, anyone? I could ask myself a question. Any questions? Okay. Well, I went ahead and did almost 2 hours worth of a review. Yay. And what I've been doing to entertain myself and entertain my students sometimes, I don't know how entertaining they find it, to tell you the truth, but I have been sharing my screen here and sticking Easter eggs on the ends of things. So, I don't have one in front of me. There you go. Here is the guitar du jour is a Gibson ES335. It's probably my favorite guitar. I love this guitar. It's a real Gibson. It's not as old as it looks. It's actually 1995, but it has aged pickups in it. These are Seymour Duncan Antiquities. And also just had natural patina on the hardware. And this is a blues guitarist guitar. I'm a big fan of the ES335. I have one painted right up there on my ceiling. And has a nice woman tone is what Eric Clapton dubbed it. Anyway, that was all. Thank you for your time, and everybody have a great day. Take care. Stop recording now.